Neumann's words, let's say what you're looking at is it's a complex system of local interactions between cells, right? And each one of these cells has 29 different states. So like you see the states here represented as colors, and every single cell responds to its immediate environment that has a pre-programmed, precise, let's say, rule set on how to act in any particular situation. What is important here for Neumann, as the father of what we will see many simpler examples coming up of cellular automata, is that, let's say, von Neumann's primary concern was to design a machine whose complexity would grow and automatically, akin to, let's say, biological organisms. He was looking into natural evolution and natural selection as the means and the main process that builds up complexity and builds up, let's say, negative entropy in the evolution of machines. So in doing so, he did what is more important here, other than like the intricacy of the video of this machine that you're looking at, is that from the beginning in this simple system, let's say the goal was an open-ended evolution that would go beyond what the programmer or the inventor of this machine ever dreamed of, right? I mean, that was the impetus, that was the goal of this type of machine. And if one looks at let's say the origins of computation, right? Like this is a goal that goes back centuries, and of course, kind of let's say it's a lofty goal that many different authors try to address. Now, this particular self-replicating machine that we're looking at consists of three parts, right? There is a description of itself, basically stored in its memory. The memory is what you're looking at, like primary yellow wall, right? As a representation of an almost infinite, like a tape. A universal constructor mechanism that can read any description and construct the machine that is encoded in that description. And then finally, a universal copy machine that makes copies of any description. We're doing a little bit of mapping here, but it's important for the purposes of interactions. One of the most famous cellular automata examples that you will find as a reference, of course, Conway's Game of Life. The three rules, actually, the most important thing that you need to remember in watching this game is that the game, again, is played on a two-dimensional grid of cells. Every single cell has two states, black or white. The rule set quickly went through your screen. I'm going to bring it back here. So every cell, every square in that grid looks around in its immediate pixel neighbors and counts. It doesn't care where they are. It just counts how many are on, how many are off, right? How many of them have a state of 1 or 0. And based on this simple addition of figuring out neighbors and a very particular balance, in fact, that this rule set has encapsulated, right, between producing black versus producing white, producing 1 versus producing 0, that balance gives rise to a very complex behavior that you see here from any, in fact, input, right? So the initial state of the grid can be pure noise, or it can be drawn, right? But then after that, every frame is automatically generated by following that rule set. Now, you see a lot of different, let's say, kind of complex explosions and whatnot, but then also every now and then we see things that start to persist, right? There is entropy built into specific forms that this game can support. And precisely because there are specific forms that resist within this context, people were able to produce highly complex machines, like the von Neumann example, through the precise design, right, of picking together these, let's say, complex little figures and putting them together into a flow chart, very similar to the type of gear or electronic flow chart, right, that you would have in a normal computer. And one little video that I love to play By the way, Conway's game of life has also been proven for its universality, right? Like you can actually build universal computers inside the game of life. And this is a nice little video. I'm gonna let it zoom out here for a second in allowing for a machine to play out its own rule set. It's a queen. Queen is an interesting reference if you've never heard of it.
So it also plays out on multiple scales.
Yes, again, this is not random, right? Like this is a very finely drawn and designed machine, right? This doesn't automatically emerge from noise. This is a carefully drawn construction that displays a specific behavior. The behavior will become very apparent in a few seconds if it hasn't already. Right. So somebody sat down here and basically modeled, right, a single pixel that has the precise behavior of Conway's game of life embedded into it as a set of gears, right? So, and that is in itself played and acted within the game of life. This is the smooth life, right? So the game of life, two-dimensional thing that I was showing you based on distance, exactly the same rule set. The only difference here is that it's applied on a really high resolution voxel grid, right? Instead of a two-dimensional grid. What is, I mean, I guess what amazes me still today, no matter how many times I watch these type of interactions, is that nothing is moving here, right? There's not even a concept of motion in what we're looking at.
State change.
There is just a super complex wave that would happen in a, in a stadium or something like that. Like there's a really simple rule set of local interactions, and these cells that are actually in fact interacting, they don't even know of the word beyond
themselves,
the radius, right? So the kind of collective behavior that is happening here that kind of appears as cell mutation and movement and everything else, it's just an epiphenomenon. We can only see it because we are standing outside of it. Like there's no difference.